Hello everyone, my name is Sivati, and for today we're going to be continuing with the topic of binary processes, which is subclassified as a medium 1. This also ties in with the topic of binary, linear, and hexadecimals. However, we're going to be diving much deeper into binary itself. So for today, we're going to be talking about 3 different topics. First one is about binary addition, second one is about binary shifting, and the third one is about 2's complement, all of which are really essential in the process of binary. Okay, so let's get right into it. So this first one is about binary addition, and as the name suggests, this is pretty much the process of adding 2 binary integers together. So before we get started on all the binary action, this is just a small note that you guys should keep in mind. If you see the number 2 at the end of each binary sequence, don't worry, this doesn't mean anything. This just shows that binary is a base 2 system, which, as we've learned from the previous lesson, pretty much means that there's 2 digits only in binary, which is 0 and 1. So if you're doing questions about binary addition where you have to manipulate the binary stuff and there's a 2 in the back, you can just neglect this because it only shows that it's a base 2 and it doesn't really affect the calculation at all. Okay? So, when you're doing binary addition, it's pretty much like adding denary or like normal numbers, your normal arithmetic math numbers, but instead we use a base 2 system. As you know, arithmetic and math uses a base 9 system from 0 to 9, which is what we use in our day-to-day lives. However, for binary, we use base 2 because binary is base 2. So let's show 2 examples here. First one is on denary, second one's on binary. Okay. So what do we do if we have this number and we want to add it? Okay. Well, the process is we start from the back, right? 9 plus 1, right? We always do that. So 9 plus 1 is 10. So we write 0 here. And the 1 goes up again on the 10th place now. So now 1 plus 3 plus 6 is 10. So this is 0 again. And the 1 is brought up again. So it's 1 plus 1 plus 7 and it's 900. Okay, so for denary, that's what we do. And in binary, it's actually quite similar, the process, except now we use 0s and 1s only. So in here, we see that we have 1 plus 1. And since this is 1 plus 1, it's going to overflow. So it's going to make 10, right? Because that's the next largest number. So 1 plus 1 equals 10. It doesn't equal 2. It doesn't equal 3. But it equals 10. Because you have to keep in mind, binary only has 2 digits, 0 and 1. And the next largest number is from 1 is 10. Because 0, 1, 10. Okay, so 1 plus 1 is 10. And since it's 10, you add a 0 here. Only a 0. Similar to denary. You add a 0. And the 1, you move it to the 10th place. But instead of moving up, programmers or people who do computer science usually like to put it small like this. Okay, so not up, tapi small like this. Okay, so this is pretty much the same as 0 plus 1 plus 1. And 0 plus 1 plus 1 is still 0. Because 0, it doesn't have a value, right? So 0 plus 1 is 1. And 1 plus 1 is 10. Right? So this is 0. And then the 1 is brought up again here. And then this becomes 1. So 0, 0, 1 plus 0, 1, 1 equals to 1, 0, 0. Okay, so here's a small little exercise. So add up the 2 binary sequences on top. See, before we only used 3 digits of binary, as in 3 how do you call it? 3 numbers of binary, 0, 0, 1. However, this time we're going to use 8, okay? An 8-bit binary. There it is. That's the term. This is a 3-bit binary. This is an 8-bit, okay? So we're going to try it with an 8-bit binary sequence here. So let's do it. So every time you want to do it, you can just draw it like this, and then we start from the back. 1 plus 0 is 1. 0 plus 0 is 0. Now here, 1 plus 1 is equal to 10. So we put 0 here, and we add 1 to the next one. And then 0 plus 0 plus 1, 0 plus 0 is 0, and 0 plus 1 is 1. So this is 1. Then 1 plus 1 is 0. 10. And we bring the 1 here. So 1 plus 0 plus 1. 1 plus 0 is still 1. And then 1 plus 1 is 10. So this is 0. We bring the 1 to the next place. 0 plus 0 plus 1 is 1. And 0 plus 0 is 0. So this is the final result. Okay? However, in a binary addition, there is this term called the overflow. And it occurs when the total from adding binary numbers cannot be stored within the registers of a CPU. And in a real context scenario, it usually results in data loss or corruption. So I'll give an example right now. Okay, so if we try to add up these two binary sequences on top, let's try to do it. So 1 plus 1 is 10. Bring 1 here. So this is 0 plus 0 plus 1, which is 1. This is 1, 1, 0, 1. Okay, this is where you guys should pay attention. 1 plus 1 is equal to 10. So we write 0 down here, and then we add 1 to the next part. Now this is where overflow happens, because 1 plus 0 plus 1 is equal to 10. Right? Because 1 plus 0 is 1, and 1 plus 1 is 10. However, where does the 1 go? Because you can only put 0 here. Where does the 1 go? And to be truthful, that we just store it next to the 0, because this results in overflow, right? Because the 1 exceeds the 8-bit register. So this becomes 9-bit, right? And this is called an overflow, because it's sort of overflowing with an additional digit, right? And yeah, as I said before, this becomes from an 8-bit binary to a 9-bit. Okay, so that's pretty much the concept of binary addition. It's more or less like that. Okay, but do keep in mind that in real life context, this one will definitely cause data loss or corruption. It's definitely going to crash your program, and that's why overflows should be mitigated at all costs. Okay, so now let's move to binary shifting. So binary shifting, as per its name, is pretty much taking any binary number and then shifting it to the left or to the right, and then we replace the empty space with a 0. Now this might seem a bit hard to imagine, so I have a small little GIF here, diagram, to show how it's actually like. So as you can see, this binary number, 8-bit binary number, is being shifted to the left by 1 spot, and then when it's being shifted, the 1, it keeps shifting here. So if we start here, the 0's getting shifted, and then 1 shifted, and then 0 being pushed, 0's being pushed again, and so on. So the number on the left keeps getting pushed. It keeps getting pushed to the left, and then it's gone. So the 0's gone here, and then the 1's gone here, then 0's gone here, and then 0's gone here. And then as we keep shifting, a new 0 is added on the right. So every time we shift a number to the left, the number on the far left is gone, and then we add a 0 at the far right, which is, per its definition, shifting it to the left or the right, and then we replace the empty space with a 0, right? So that's pretty much how binary shifting works, and this correlates with multiplication and division using binary. Okay, so before we get to that, let's try a small little exercise first. Let's shift the binary register, one register to the left. So we have this, and let's shift it to the left by 1 spot. So if we want to shift it to the left, it's very similar to the GIF that I showed you guys before. What we do is the 1 here, we move it to the left, so that means it's gone, right? And, the 1, we remove it, and then we move everything to the left, and then we add a 0 at the end, right? So it's pretty much the same as pushing this 1 over. Okay, so the 1 is gone, and then the rest follows. Okay, so this 1 on the second spot takes over the first position. It moves to the left, and then at the far end here, we add a 0. Okay, now this is also a similar process, except now we're doing it to the right. So if we do it to the right, the far right digit is gone, everything shifts to the right by 1 spot, and then we add a 0 at the end. Like this. Yeah. Okay, so why do we have the binary shift? As I said before, because it represents multiplication and division. So if you want to shift to the left, it represents multiplication. If you want to shift to the right, it represents division. And this makes sense, because if you see here, when you try to shift it to the left, you're pretty much adding more value to it. You see, if the one's being pushed here, it adds, it overflows, you could say. So the one's being moved to the 9th bit here. So it's actually adding value. If you convert it to denary, it's adding value. However, if you try to shift it to the right, it's actually losing value, because everything is shifted to the right, and then the far left is replaced with a 0. And this correlates to the concept of weight factors, where if this is a 0, then the weight factor of the digits on the far left isn't counted, right? So this digit is 128, right? And if it's 0, then the 128 isn't counted. So the denary value will of course be less, right? That's why it's dividing. So I think that's a good analogy to help understand why it's left and right instead of just simply memorizing. Okay, and this is something that you guys should keep in mind. So when you multiply a binary value by 2, it's pretty much the same as shifting to the left by 1 register. Right? Multiplication is to the left, and multiplied by 2 is 1 register. Multiplying by 4 is shifting to the left 2 registers, and multiplying to the left by 6. Multiplying by 6 is moving the binary 3 registers to the left. So if you notice, these are multiples of 2, right? So if it's 2, then it moves to the left by 1 register. 4 is 2, and 6 is 3. And it keeps following this pattern. So if it's 8, then it moves to the left by 4, and so on. And division is the same, except now it's to the right. So dividing by 2 is moving to the right by 1. Dividing by 4 is moving to the right by 2. And dividing by 6 is moving to the right by 3. Right? And yeah, these are all multiples of 2. So let's try this. So let's try to multiply the binary by 4. Okay, if you want to multiply this binary by 4, we have to follow the rule that if it's multiplied by 4, then it shifts to the left by 2 registers. So now let's shift it to the left by 2 registers. So if you shift to the left by 2, it will become like this, right? If you do the process before, you should get this. Okay? And this is what I want you guys to notice. Okay? If you convert the binary on top to denary, this becomes 6. Use the principles of weight factor. This is 4 and this is 2. So 4 plus 2 is 6. And if you convert the binary below here into denary, this actually becomes 24. What do you notice? 6 to 24. This is multiplying by 4, right? And this is the same as multiplying the binary by 4. So the denary and the binary actually correlate with one another, you see? And that's what's so interesting. So actually, you're pretty much like multiplying like normal. So if you're multiplying denary digits like normal, like 6 multiplied by 4 is 24. But now, you're converting it into binary form. So you're multiplying the binary inside of the denary. So they actually correlate with one another, which is something that I want you guys to understand, to fully grasp in the topic of binary. Binary is similar to what we use in our day-to-day life, like normal counting arithmetic. Here's another example. If you divide this binary by 2, you need to shift it to the right by 1, right? So you get this, okay? And then if you convert it to denary, this becomes 42 and this becomes 21. And this is dividing by 2. So it follows the principles again. However, this is the only exception. So let's try to divide this binary by 2, okay? So if you divide this binary by 2, you have to shift it to the right by 1. So you get this. Okay, but what do you notice? On the top, the binary has a denary conversion of 3. Whereas below here, the denary is actually 1. And this doesn't make sense because if you divide 3 by 2, it's 1.5. So why is the denary 1? And the reason is because in this form of binary, we're not storing decimals, so the fraction is discarded. What you should notice is that binary doesn't store decimals. It doesn't store fractions. It only stores integers. So denary can't be 1.5 or 1.75. It's only 1, 2, 3, 4, 5. It's only like whole numbers, okay? So no decimals. Since 3 divided by 2 is a decimal, it can't store that 0.5. That's why the denary is simply 1. It's pretty much rounded, right? It cannot store any decimals. So 1.5 becomes 1. So you have to be careful as well when using denary, okay? If you try to divide a denary, and then it becomes a decimal, then you have to be careful when converting it to binary, okay? Because it may be different. Okay, now let's move on to 2's complement. And 2's complement is pretty much a way to represent negative numbers in binary so that a computer can read them accurately. So yeah, negative numbers. And this allows for subtraction, okay? And this is some additional notes. It can also help detect overflow by examining the carry into and out of the signed bit. However, you don't need to understand this at the moment. All you need to know is that 2's complement is pretty much a way to represent negative numbers in binary. And here's an example. We know that the denary 5 in binary is 0, 0, 0, 0, 0, 1, 0, 1. But how about negative 5? if we want to find the binary of -5, you have to use the 2's complement of 5, or the negative of 5. Okay, but how do you find the negative of 5 in binary? So to find the 2's complement, you have to simply simply invert each bit and then add 1. What does this mean? So basically, inverting each bit means that 0 here becomes 1 and 1 becomes 0. So you do this to each one. So 0 becomes 1, so it becomes 1 1 1 1 1 0 1 0. That's called inverting. And then you add 1. So this is binary addition. You add 1 and this becomes this. And this is the 2's complement of 5. This is -5. Okay, those two steps are very crucial if you want to convert a denary into its 2's complement, a binary into its 2's complement. Okay, so knowing this, we can actually subtract binary numbers. So here's an example. Find the result of 23 subtracted by 17 by converting to binary as the process. Okay, so 23 is subtracted by 17. Let's write that down first. Okay, if you notice, 23 minus 17 is actually the same as 23 plus -17, right? So basically, what we're doing is binary addition of 23 with its 2's complement, the 2's complement of 17. So the 23, we need to convert to binary first, and then the 17, we have to convert to binary via 2's complement, since this is -17. So let's do that. So 23 in binary is this, and 17 is this. So if you want to find -17, you have to do 2's complement by first inverting. So 1 1 1 0 1 1 1 0, and then you add 1. So it becomes this. And then now, if you want to find 23 minus 17, you just need to add these two together. So it's 23, which is 0 0 0 1 0 1 1 1, plus 1 1 1 0 1 1 1 1. Okay, and if you do this, you get this number right here, 1 0 0 0 0 0 1 1 0. Okay, and if you know this, this becomes an overflow. It overflows and becomes a 9-bit. So usually in a computer system, they would only recognize the first 8 bits. So usually they would only take into account this green part right here. And this is pretty much proving. If you consider the green part, then the mathematical operation actually makes sense. See, because 23 minus 17 is of course 6, and this right here, the binary, is equivalent to 6, because using the principles of weight factor, this is 4 and this is 2. So this is a match. However, if you include the 1 right here, the one that overflows, it's definitely gonna exceed 6, right? It's gonna be 262, and that is not correct. That's why we usually take into account only the green part right here, because it satisfies the mathematical operations. It makes sense. So yeah, that is pretty much the concept of 2's complement. Okay, that is all for today's material. If you guys would like additional practice, maybe worksheets, you guys can of course DM me. My socials are in the description, and for the next class we will dive deeper into pseudocoding and coding in general. So yeah, that is all from me, and thank you for watching.